Welcome to our short explanation video about the polynomial regression. Our task was to program the polynomial regression, which was already shown by another group in the previous video, in Python in a Jupyter notebook. To program the polynomial regression, we are following a step-by-step guideline which was already given. The first thing we needed to do is to load our data and inspect it. In the second step, we created our design matrix, which was a vendor Moore matrix. After we created our design matrix, we then had to calculate the Moore-Penrose-Pseudoinverse of this design matrix. In the next step, we wanted to minimize the squared error in our given set of measurements. As a last step, we then used this computed coefficients or beta coefficients or weight to construct the polynomial we were looking for. And in the last step, we plotted different polynomials of different degrees to see how these polynomials fit to our given data. After some usual imports, we had to load the given data set and start the independent variables in our variable x and the dependent variables in our variable y. To get familiar with our data, we had to look at our values. You see our given data points here in blue. You see on the x-axis the independent variable and on the y-axis the dependent variable as we constructed here before. To familiarize even further with our dataset, we had a look at the given target function, which was the underlying function creating our data points with some added noise. You can see the underlying target function here.
The first actual step to compute a polynomial regression is to create a design matrix, which is called Vandermonde matrix in our case, which looks like this. For that, we define the function polydm, which gets the parameters x and m, where m is our degree and x are our values. First, we create our output matrix, which is called design matrix here, and fill it with zeros. Our matrix has to be the same length as x and m+1 rows. m+1 is important because we have m degrees, or our degree is m, and the first row has to be only 1. Now that we got our matrix, we fill each of the rows, so for every row in the range of m+1, with our value x. So our whole independent variables are getting stored in each row. Afterwards, to get a row with ones, we change all the values of the first row to 1. In the next step, we use the function denumerate of the NumPy package to iterate over all the entries of our design matrix, so all columns and all rows. For each of those entries, we define our exponent as index of 1 or as our row number. Then we change the entry of the design matrix at that index to the original entry to the power of the exponent. At last, we just return our design matrix, which should look like this. To visualize this even more, we created an example array, which is very simple. We got the data points 1 through 5, and we want to get a design matrix of degree 3. And if we run this, we get a matrix like this, where the first row is just containing ones, and the second row contains just the values, and each row after that contains the values to the power of the exponent, which is here 2 and here 3.
In the next step C, we had to compute the Moore-Penrose-Pseudoinverse of our design matrix A. To do so, we have given this formula. The T is standing for the transpose of a matrix, and the -1 is standing for the inverse. As you can see here, we just modeled the function which is given here, where A transposed is A t, A to be inversed is the multiplication of our transposed A and A, as here. A inversed is this whole term here. And our resulting pseudo-inverse is the multiplication of the resulting matrix here with the transposed matrix here. You can see the last matrix multiplication in this step, and the resulting matrix is our pseudo-inverse. So in the next step we are about to estimate our parameters, here called alpha of I. These are the parameters we talked about before when we talked about to minimize the squared error of our n-degree polynomial. This whole thing is always in consideration of our data. To estimate these parameters, we are using this formula, where this is our design matrix and this is the pseudo-inverse which we computed above. The y corresponds to the vector of our dependent variables, which we already stored in the capital Y. To do so, we simply had to call our predefined function polydm to get our design matrix, to call the function pseudo-inverse to make a pseudo-inverse of this design matrix, and to multiply the inverse of the design matrix with our dependent variables.
For the next and almost last step, we map our parameters onto our data. We therefore define the function polynom, which gets the parameters x and w. First, we create an output array with the same length as the input array x. For every entry in x, the y value is computed as the sum of beta coefficient times the value of x to the power of the corresponding exponent. So basically, our given polynomial function or our assumed model. In the last step, we want to compare our target function, which is used to generate our data. In this graph, you can see our data as the white dots and our target function as the blue line. The polynomials of degree 1 and 2 are this line, where the polynomial of degree 1 is really hard to see because it's almost completely covered by the polynomial of degree 2. The polynomial of degree 10 is the red line.